We are not just learning Terraform, we are going to think like a solution architect. Many engineers start from code, but real-world systems do not start with the Terraform files or AWS services. They start with a business problem. A company wants to launch on an online platform. Customer expect it to work all the time. User comes from everywhere. Traffic can certainly grow. Our job is to transform those ideas into a real cloud system. So in this season, we will walk through the full journey from business needs to technical thinking to cloud architecture, and finally to Terraform implementation. By the end, we will understand why infrastructure exists, not just how to write it. Let's begin with the business perspective. Imagine you are meeting a company founder. They don't say, please create a VPC and an auto-scaling group. Instead, they say, our service must always be available. Users from everywhere should access smoothly. We cannot afford downtime. Traffic may certainly increase. Notice something important. These are business goals, not technical instructions. Your responsibility as an engineer is to understand the meaning behind this work, because architecture decision always start here, not inside AWS. The architect's job. This is the more important skill of a solution architect. We translate the idea step by step. First, the business language, then technical requirement, then architecture design, finally infrastructure code. In Terraform is actually the last step, not the first. Many engineers jump directly into coding, but a strong architect asks, what problem are we solving? The translation process is called requirement translation. If you master the skill, you can design system, not just deploy resources. Requirement analysis. Let's decode the business language. When a company say 24/7 availability, they actually mean high availability architecture. When they say nationwide access, they mean user must reach servers reliably from many locations. No interruption means the system must survive failures. Traffic spike means the system must grow automatically. This table is where architecture truly begins. Every AWS service we choose later comes directly from this meaning. Architecture is not guessing, it is a logical translation. High availability requirement. Imagine running your entire business on one server. If the server fails, everything stops. This is called a single point of failure. A production system must avoid this. Instead, we deploy server across multiple availability zones. A load balancer distribute traffic. Auto scaling replaces unhealthy instances automatically. Now failure becomes normal, and the system keeps running. This is true high availability. Traffic distribution. Users should not know which server they connect to. They should see only one entry point. The entry point receives on request and decides where traffic goes, which servers are healthy, how to balance a load efficiently. This is exactly what an application load balancer does. It becomes the smart front door of our system. Zero downtime strategy. Downtime usually happens when one layer fails, so we protect every layer. If a server fails, auto-scaling replace it. If an instance become unhealthy, ARB stop sending traffic. If a database fails, Multi-AZ RDS switches automatically. Each layer protects the net. This layer resilience is what makes production systems stable. Handling traffic spike. Imagine a marketing campaign goes viral. Traffic increases 10 times. Manual scaling is too slow. Auto scaling monitor metrics like CPU or request. When load increases, never server launch automatically. When traffic drops, server terminate to reduce cost. This gives both performances and efficiencies. Data and storage. Application servers can disappear anytime, so we never store important data inside them. Database live in RDS with failover protection. Files such as images are lost or upload row to S3. IAM browser allow secure access without password. This separation makes system scalable and secure. Finally, architecture. Now we can see the complete system. Traffic enters through the load balancers. Request go to scalable application servers. Data is safely stored in the managed services. Each component exists because of a business requirement. Nothing is random. This is how architect design system. Network layer. Security group layer. Demo app. We organize everything using Terraform. Modules represent reusable infrastructure components, environment separated development, staging, and production. This structure allows teams to scale safely and collaborate efficiently. Good architecture is not only about AWS design, it is also about clean infrastructure code. I will briefly introduce a highly available and scalable cloud infrastructure architecture. The system runs inside a VPC deployed across multiple availability zones, ensuring high availability and failure and fault tolerance. Incoming user traffic is handled by an application load balancer, which distributes requests across multiple application servers. These servers are managed by an auto-scaling group, allowing the system to automatically scale based on traffic demand, while a long template ensures consistent server configuration. The database layer uses Amazon RDS Multi-AZ mode for automated failover and data reliability. Static files and backup are stored securely in Amazon S3 with access control through IAM roles. Administrative access is provided through a version host, and a NAT gateway enables private instances to access the internet securely without being publicly exposed. Overall, this architecture provides a secure, scalable, and production-ready environment following cloud best practice. Now we find out VPC module, variable, output, and main. In this Terraform configuration, we are building the foundational network infrastructure on AWS, starting with a VPC. First, we create a VPC using a configurable CIDR block defined by variable. The DNS support and DNS host names are enabled so that resources inside the network can communicate using domain names instead of only IP addresses. This is important for modern cloud applications and service discovery. Next, we attach an internet gateway to the VPC. The internet gateways allow resources in public subnets to communicate with the internet, making it possible for users to access public services such as the web servers. After that, we create two types of subnets, public and private subnet. Instead of hard code the number of subnet, Terraform dynamically created them based on the number of availability zone provided. Each subnet receives its CIDR calculated automatically using the CIDR subnet function. Public subnet configured to automatically assign public IP addresses to instances when they launch, which makes them reachable from the internet. Private subnet, on the other hand, do not expose resources directly, providing an additional security layer for internal services like database. When we then create a public role table, This role table defines a default role that send on outbound traffic to the internet gateway, enabling internet connectivity. Finally, the role table is associated with on public subnet, ensuring that any resources play in those subnet can access the internet through the gateway. Overall, this Terraform code creates a scalable multi-availability joint network foundation that separates the public and private resources while following AWS best practice for security and availability. Now we find out ALB. Variable output and admin file. In this Terraform configuration, we are setting up an application load balancer to handle incoming web traffic and distribute it safely across application servers. First, we create a security group for the load balancers. This security group allows incoming HTTP traffic on port 80 from anywhere on the internet, which means users can access the application through a web browser. At the same time, outbound traffic is fully allowed so the load balancers can communicate with backend services without restriction. Next, we create an application load balancer which is internet traffic, internet facing, and deploy across multiple public subnets. This ensures high availability because the traffic can be brought through different availability zones. If one becomes unavailable, the load balancer also has HTTP per 2 enabled, improving performance and connection efficiencies for modern web clients. After that, we define a target group which represents the backend application servers that will receive traffic from the load balancers. The target group listens on port 80 using the HTTP protocol and include health traffic configuration. The load balancers periodically check the root path of each server and only send traffic to instances that respond successfully, ensuring reliability and automated failure handling. Finally, we create a listener on port 80. The listener waits for incoming HTTP requests and forward them to the target group, allowing traffic to flow smoothly from user to healthy backend instances. Overall, this configuration builds a scalable and resilient traffic entry point that improve availability, balance load efficiently, and ensure users are always the road to healthy application server. We find out about autoscale group. In this Terraform configuration, we are building a scalable application layer using a long template and an auto scaling group. First, we define a long template which acts as a blueprint for EC2 instances. It specifies the Amazon Merchant image instance type as a key security group and IAM instance profile. This ensures that every server launched by the system has the same configuration and permissions. The template also supports optional root volume customization, allowing you to control disk size and storage size when it. In addition, user data is provided so that the instance can automatically run initialization script during startup, such as installing software or configuration the application environment. Next, we create an auto scaling group which automatically manage a fleet of EC2 instances across provide subnets in multiple availability zones. The group maintains a desired number of running instances and can scale up or down based on demand. It is connected to an application load balancer target group, ensuring that traffic is route only to asset instances. Health checks are enabled, so unhealthy instances are automatically replaced. Instances refresh is configured with a rolling strategy, meaning update can be deployed gradually without downtime by replacing instances in batches. To enable automatic scaling, we define a target tracking scaling policy based on CPU utilization. When CPU usage increases beyond the defined target, new instances are launched automatically, and we demand decrease as instances are terminated to optimize cost. Finally, we configure a security group for the application server. It allows HTTP traffic only for the load balancer and SSA asset only from the bus host, while outbound traffic is allowed through another gateway from security internet access. Upfront, this configure create a secure cell health link and automatically balance scalable application layer, and that follow cloud-based practice for reliability and efficiency. Now we find out RDS variable file output. In the Terraform configuration, we are provisioning a secure and highly available database layer using Amazon RDS. First, we create a DB subnet group which defines where the database will run inside the network. The subnet group includes private subnet across multiple availability zones, ensuring that the database is isolated from public internet access while still supporting high availability. Next, we configure a security group specifically for the database. This security group allows inbound traffic only on port 3306, which is the default MySQL port, and only from the application server's security group. This means the database cannot be accessed directly for the internet, providing strong network layer protection. outbound traffic is allowed so that database can communication with the required AWS service when necessary. After that, we create the RDS MySQL instances itself. The database run using configuration instance size, and credential defined to variable, making the infrastructure reusable across different environments such as development, staging, production. Multi-AZ development is enabled, which automatically creates a standard database in a not availability zone. If the private database becomes unavailable, AWS performs automatic changeover, minimizing downtime and improving reliability. Finally, the database is associated with the subnet group and security group we defined earlier, ensuring proper network placement and secure communication with the application layer. Overall, this configuration build private, secure, and highly available database system that follow AWS best practice from production environment. Now we find out S3. In this Terraform configuration, we are creating an Amazon S3 bucket for storing application data in a secure and reusable way. First, we use a data source called AWS Controller Identifier to retrieve information about the user or the current AWS account. Specifically, it allows Terraform to automatically obtain the AWS account ID of the user and role running the deployment. It has auto generate unique resource names dynamically without hard-coding values. Next, we create an S3 bucket. The bucket name is built using the project name, environment, and the AWS account ID, including the account ID is important because S3 bucket names must be globally unique across on AWS account worldwide. By constructing the name dynamically, the same Terraform code can be reused across multiple environments, such as development, staging, and production, while avoiding naming conflicts. Overall, this configuration ensures that the storage resource is unique, identified, environment aware, and easily reusable as part of an scalable infrastructure setup. Next, we find out the IAM. In the Terraform configuration, we are creating an IAM roles that allow EC2 instances to securely access AWS services without using hardcode credentials. First, we define an IAM role specifically for EC2 instances. This role will be assumed by EC2 whenever an instance is launched. Instead of storing as a case inside the server, AWS temporarily provides secure permission through this role. To avoid EC2 to use the role, we create an assume role policy using an IAM policy document. This policy implicitly trust the EC2 service by allowing the action. as the assume role. In simple terms, this tell AWS that EC2 instances are allowed to take on this role and inherit its permissions. Next, we attach a managed policy called Amazon S3 full access to this role. This grant EC2 instances permission to interact with Amazon S3, such as a login file, downloading access or storing backup. Finally, we create an IAM instance profile, which acts as a bridge between the IAM role and the EC2 instances. When the instances launches, this profile is attached, automatically enabling the application running on the server to securely access S3 without managing current or manual. Overall, this configuration follow AWS security-based practice by using role-based access control, improving security, scalability, and operational simplicity. Now we file down up. In this Terraform configuration, we are enabling a secure internet access for resources located in a private subnet. First, we create an elastic IP address, which is a static public IP provided by AWS. This IP address will be attached to the NAT gateway so that outbound traffic from private resources can reach the internet using fixed public identity. Next, we create a NAT gateway inside a public subnet. The NAT gateway acts as a bridge that allows instances in private subnet to access the internet for tasks such as downloading, upload, installing a package, or connecting to external API, while still preventing inbound internet traffic from reaching them directly. After that, we define a private route table. This route table includes a default route, the send on outbound traffic, meaning any destination outside the VPC through the NAT gateway. Finally, we associate this route table with on private subnet. This ensures that every resource play in those subnet automatically use the NAT gateway whenever it needs internet access. Overall, this configuration allows private instances to communicate securely with external services while remaining protected from direct public exposure, following AWS networking best practice. Now we find our version. In this Terraform configuration, we are creating a version host which provides secure administrative access to resources inside a private network. First, we define a security group for the version server. This security group allows inbound SSA access on port 22, but only from a specific IP address defined by a variable. This restriction ensures that only authorized administrator can connect to the server, significantly improving security. Outbound traffic is fully allowed so that version hosts can communicate with other resources and external services when needed. Next, we create an EC2 instances that act as the version host. The instances is alone inside a public subnet, allowing administrator to connect to it from the internet using SSA. A key pair is specified for secure authentication and the previously created security route. It attached to control network access, and one connects to the button host. Administrator can securely access a server located in private subnets without exposing those internal system directly to the internet. Overall, this configuration establishes a control and secure endpoint into the infrastructure following AWS security best practice by minimizing public exposure while maintaining operational access. Thank you.